Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 8, Lesson 8 on the zero product law. Now, without being too hyperbolic, this is one of the most important topics in all of algebra. Like literally, the zero product law is one of the most amazing things in algebra, and you will continue to see it in algebra, geometry, algebra 2, pre-calculus, calculus, as long as you stay in math. This particular thing that we're going to look at today, for the first time, this will be the first time that you will have seen it, is really, really essential and pivotal. So let's jump right into it and try to understand what this zero product law is. Now first, let's start off with the zeros of a quadratic function, a function. Now the zeros of a quadratic function are important. They're critically important. They have an interesting tie to the factors of a quadratic, all right? So let's kind of take a look at a quadratic function, exercise number 1. Consider the quadratic function y equals x squared minus 2x minus 3. Its graph is shown below. Letter A, what are the zeros of the function? Write their x values and circle them on the graph. All right, so this should be no problem. Why don't you go ahead and figure out what the zeros are, circle them, and then write down their x values right here. Pause the video for a moment. All right, well, the zeros of a function are just the locations where the y value is equal to 0. The x values where the y value is equal to 0. Those occur on this graph right here and right here. That happens to be at x equals -1 and x is equal to 3. Awesome. All right, so big deal, all right? But now we want to see how those two values are somehow related to the factors of this quadratic expression. So take a look at letter B. Write the expression x squared minus 2x minus 3 in factored form. All right, so like literally, I'm really asking you to factor the right-hand side of that function. So take a moment. Shouldn't take you very long. This should be an easy trinomial to factor. Go ahead and figure out what its factors are. All right, well, let's do it. Right, I'm thinking about two numbers that have a product of -3 and a sum of -2. Well, I love the number 3 because there's only there's only two positive numbers, positive integers. I have to keep refining what I'm saying. There's only two positive integers that have a product of 3, and those are 1 and 3. Now, in order for it to be a -3, of course, it's got to be a -3 and a +1 in order to have a sum of -2. So x squared minus 2x minus 3 is equivalent to x plus 1 times x minus 3. Right? X plus 1 times x minus 3. Now, just take a look at these two factors and take a look at these two zeros. Here I've got x plus 1, here I have x equals -1. Here I have x minus 3, here I have x equals 3. So, why is this happening? Well, let's take a look at letter C. Substitute your values from A into the factored form of x squared minus 2x minus 3 and show why each must be a zero of the function. Okay, well, I want you to keep in mind that this is really y equals, right? So if I actually substituted those in here, let's first do x equals -1. All right, when I substitute x equals -1 into that expression, I get this. Now, -1 plus 1 is 0, and -1 minus 4 is -5, and 0 times anything is equal to 0. All right, so when x equals -1 goes in, 0 comes out. Y equals 0. On the other hand, if I put x equals 3 into the expression, I get 3 plus 1 times, wait a second, I don't know why I have a -4 there. I apologize. That was silly. That should be a -4 there. Apologize for that. But if I put 3 in, then I get 3 plus 1 times 3 minus 3, and that's 4 times 0, and that's also 0. Right? So why are these two values equal to 0? Well, they're equal to 0 because each one of them makes one of the two factors equal to 0, and whenever you multiply anything by 0, you get 0. Now, that's not quite the zero product law, though. Let's take a look at what that is. All right, the zero product law. The last exercise illustrated one of the most important and simple concepts in all of mathematics. If an expression is factored and equal to 0, then one of the factors or both must be equal to 0. In symbolic form, if a times b is equal to 0, then either a is equal to 0, or b is equal to 0, or both are equal to 0. Now, I really want to step back for a moment before we get into exercise 2 and really make you understand this. If I said, hey, I've got two numbers that have a product equal to 12, what are the two numbers? Well, you could say, that's 2 and 6, 3 and 4, 1 and 12. You could even get a little crazy. You could be like, it's -3 and -4. Or you could even go fractional. You could be like, well, it's 1/2 and 24. Those two have a product of 12. But if I told you that two numbers have a product of 0, one of those numbers has to be 0. It has to be. You cannot multiply two non-zero numbers together and get 0. It's something that is particular about 0 that is not true of any other number. Even of like a special number like 1, right? If I had two numbers whose product was 1, one of them doesn't have to be 1, right? I could have 5 times 1/5, that's equal to 1, or 2 times 1/2, that's equal to 1, right? But 0 is unique in all of numbers by the fact that if a product is equal to 0, then one part of the product or both must be equal to 0. I have to throw in or both because, of course, 0 times 0 is also 0. So how does the zero product law work to help us find solutions? Well, let's take a look at exercise number 2. Use the zero product law to find all solutions to each of the following equations. All right, well, if I've got an equation that looks like x plus 7 times x minus 2 is equal to 0, and you have to really, right, that's a product. X plus 7 times x minus 2 is equal to 0, well, then I know that either x plus 7 could be equal to 0, or x minus 2 could be equal to 0. And the great thing is, as soon as I write those two down, solving them is a piece of cake, right? To solve this one, I just subtract 7 from both sides, and I get x equals -7. And to solve this one, I add 2 to both sides, and I get x is equal to 2. Now, be careful. I get some people with the zero product law who get a little bit flip with it, and they say things like, well, I just look inside of the parentheses, and when I see a +7 there, I know that the answer is -7. And when I see a -2 there, I see that the answer is +2. And that does work if you've got binomials in here where the leading coefficient on each one of the binomials is equal to 1. But the zero product law certainly works in a situation like this. In letter B, I have 2x minus 1 times 3x plus 4 is equal to 0. Since I have a product equal to 0, either the 2x minus 1 could be equal to 0, or the 3x plus 4 could be equal to 0. Now, these two equations take a little bit more work, but only a little bit more, right? I would then get 2x is equal to 1, divide both sides by 2, and I'd get x equals 1/2. In this equation, I'll get a negative, subtract 4 from both sides. 0 minus 4, be careful there, is -4. Then divided by 3, and I'd get x equals -4/3 or -1 1/3, however you'd like to express it, right? This is an amazingly important idea, right? If I've got a factored expression set equal to 0, I can solve that equation by taking each factor and setting it equal to 0, because when the product of two or more things is equal to 0, one of those things has got to be equal to 0. All right. Now, of course, this brings up a very interesting fact. What if the thing isn't factored and set equal to 0, right? So the zero product law can be used to solve quadratic equations as long as they can be factored and are set equal to 0. Okay, so let's take a look at some that aren't already factored. Exercise number 3. Find the solutions to each of the following equations by using the zero product law. Sometimes you will be instructed to solve by factoring. All right, now before we kind of move on and do this, I want to point out that letter A, x squared plus 4x minus 12 equals 0, is something that we would have solved in the last few lessons by using completing the square. So the zero product law is actually an alternative to completing the square. Now that doesn't mean that if you like this one better, you can forget about completing the square. Most state assessments in Algebra 1 require you to know both how to solve a quadratic by factoring and how to solve a quadratic by completing the square. So don't think that they're kind of like interchangeable and, oh, I can just pick and choose. Sometimes you can, but many times they will literally say, solve this quadratic by factoring or solve this equation by completing the square. So anyway, let's look at how we solve this now by factoring. All right, since this equation is equal to 0, I can look at the left-hand side and I can simply replace it by its equivalent in terms of factoring. Now, how do I factor that trinomial? Well, I need two numbers that have a product of -12 and have a sum of +4. And those two numbers are +6 and -2, right? So I can factor the left-hand side of this equation as x plus 6 times x minus 2 equals 0. As soon as you have the product of two or more things equal to 0, you can set each one of those things equal to 0. So I'll do x plus 6 is equal to 0, and x minus 2 is equal to 0. Subtract 6 from both sides, and I'll get x equals -6. Add 2 to both sides, and I'll get x equals 2. X equals 2. Again, never forget, right, that even though this does rely on a little bit of a gimmick, not so much of a gimmick as a mathematical fact about the number 0 and products, right? Never forget, you can take these numbers, put them back into the original equation, right? And see that it makes it equal to 0, or it makes the equation true. Like if I put 2 in there, right, I'd get 2 squared, which is 4, plus 4 times 2, that's 8, plus 4 is 12, and 12 minus 12 is 0. So yeah, it works. I won't even go there with the -6, but it does. Now, it should be very easy to see why it works once you've factored the equation, right? If I put -6 in here, that's 0. And if I put 2 in there, that's 0. And 0 times I don't care what the other one is 0. Now, what we have to be ready with the zero product law is any of our types of factoring. Any type of factoring could come up with the zero product law. So for instance, let's take a look at letter B. Here we've got 2x squared minus 14x is equal to 0, right? Now, the zero product law is only helpful for me if I can factor that left-hand side. Well, this time I don't have a trinomial, so that's out. I also don't have the difference of perfect squares, right? I don't have like x squared minus 9 or x squared minus, I don't know, 36 or whatever. But I do have a GCF, right? Because there's a 2 that goes into both 2 and 14, and there's an x that I can also factor out. So this is just simply GCF factoring on this one. And in fact, I can factor this as 2x times x minus 7 equals 0, right? Now, I can really look at the 2x as if it is attached to one another, right? So I can think of my two factors as being 2x and x minus 7. So what do I have at this point? Well, either 2x is equal to 0 or x minus 7 is equal to 0. So I'll divide both sides by 2. Be careful here. 0 divided by 2 is simply 0. All right, and here, simple enough, I'll add 7 to both sides. And that's it, right? X equals 0, x equals 7, both of which you can easily check to see if they're solutions. All right, now, again, keep in mind, we've got three types of factoring. We've got trinomial factoring, which we saw in A, right? We've got GCF factoring, which we saw in B, and we've got the difference of perfect squares factoring, which we're going to see in C, right? In letter C, we have x squared minus 25 is equal to 0, right? Now, by the way, this one would be very easy to solve using inverses, right? I could add 25 to both sides. I'd get x squared equals 25. And then I could take the square root of both sides and I'd get x equals plus or minus 5. No problem with that. But we just want to like illustrate this with the zero product law as well. So how does x squared minus 25 factor? Well, it'll factor as x minus 5 times x plus 5. And that's the way the difference of perfect squares always factors. It always factors into the product of two conjugate binomials. Now I can take x minus 5 and set it equal to 0, and x plus 5 and set it equal to 0. Add 5 to both sides, and I get x equals 5. Subtract 5 from both sides, and I get x equals -5. And again, that would be very, very easy to do with what we did a couple lessons ago, just using, forget about completing the square, right? We could just do this using pure straight up inverses. I would probably never use factoring to solve this, but you know, we're doing it right now. Now, the final type of factoring we saw was complete factoring, right? And that's where we first factor out a GCF, and then maybe we do a little bit more. So let's take a look at that in letter D. Let's take a look at this one up close, right? Letter D, I have 2x squared minus 26x plus 60 equals 0. And one thing I should notice is that the 2, the 26, and the 60 all have a common factor, a GCF, of just the number 2. So the first thing I'm going to do is factor that 2 out, right? And when I do factor the 2 out, I get x squared minus 13x plus 30 is equal to 0. All right, so that's just my first step. Now I want to completely factor this thing. So now I want to look at x squared minus 13x plus 30, which is obviously a trinomial. And I want to find two numbers that have a product of positive 30, right? And have a sum of negative 13. Keep in mind, both of those numbers have to be negative in order to have a positive product and a negative sum. It'd be very, very easy to think, oh, negative 15 and positive 2, right? Because negative 15 and positive 2 would have a sum of negative 13, but they wouldn't have a product of positive 30. So in fact, this actually factors as x minus 3 times x minus 10 equals 0. Now, let's take a look at this and pause for a minute before we finish up. I've got 2 times x minus 3 times x minus 10 is equal to 0. So one of those three factors, and there are three factors. There's a factor of 2, a factor of x minus 3, and a factor of x minus 10. One of those three factors has to be equal to 0. For a moment, just for a moment, I'd like you to think for a moment, which of those three factors could never be equal to 0? Yeah, the number 2, right? The number 2 can't be equal to 0, and that's okay. I don't need it to be equal to 0. I need these two to be equal to 0, but that wouldn't have any effect. The 2 has no effect on this at all. In fact, a lot of teachers will put down this: 2 can't be equal to 0, right? So that factor can't be equal to 0. It can't be. Not even on its worst day is 2 equal to 0, right? On the other hand, x minus 3 could be equal to 0, and x minus 10 could be equal to 0, in which case add 3 to both sides, and I'll get x is equal to 3, add 10 to both sides, and I'll get x is equal to 10, right? But the 2 is really irrelevant, and the last thing I'd ever want you to do is get 3 and 10 and go, oh, 3 and 10, and now I got to multiply them by 2, so I'm going to get 6 and 20. Well, I promise you this: x equals 6 and x equals 20 would not make this equation equal to 0. Try it. You know, if you put 6 in here, you'd get 2 times 6 minus 3 times 6 minus 10. None of them are equal to 0, right? So if I put 20 in there, same thing, right? All that factor is just a factor that can't be equal to 0. The only factors that can be equal to 0 are the ones that involve x's, or whatever your variable is. All right, let's do one more problem. Let's tie this into a graph. Exercise number 4. Find the zeros of the quadratic function y equals 3x squared minus 6x minus 24 algebraically. Then verify your answer by using your calculator to sketch a graph of the parabola using the window indicated on the axes below. Clearly mark the zeros on the graph. All right, great. So whenever we want to find the zeros of a function, as opposed to just solving a random equation, what we do is we set y equal to 0, because that is what the zeros of a function are. The zeros of a function are where y is equal to 0, so algebraically, we want to solve this equation. Okay, great. Now, in the last exercise, right, I was like, oh, let's factor a 2 out. And you can actually do the same here, right? There's a 3 that can be factored out of this, or you could start by dividing both sides of the equation by 3. So let's actually start by doing that. Remember, I mean, there's the division property of equality. So since 3, 6, and 24 can all be divisible by 3, as well as 0, let's just start with that. Right? Let's make our lives easy and get rid of the 3 that way. Now 0 divided by 3 is 0, and don't forget to distribute the division. 3 divided by 3 is 1, 6 divided by 3 is 2, and 24 divided by 3 is 8. So I've basically just made that equation simpler. All right? Now what I'd like you to do is pause the video and finish solving this quadratic equation by factoring that right-hand side and setting each of those factors equal to 0. Pause the video now and go ahead and do that. All right, well, let's do it. I'm looking for two numbers whose product is equal to -8 and whose sum is equal to -2. Those will be -4 and +2. All right, so if I do x minus 4 and set it equal to 0 and add 4 to both sides, I get one of the zeros is equal to 4. And then if I take x plus 2 and set it equal to 0, subtract 2 from both sides, x will be equal to -2. So those should be the two locations on my graph where y is equal to 0. In other words, these should be my x-intercepts. Let's plot them right now before we even bring out the graphing calculator. Right? X equals -2 would be right here, and x equals 4 would be right here. Let's hope that's correct. I'm going to exit out of here. Okay, I'm going to open up my graphing calculator. All right, let's put that function in. That function was 3x squared minus 6x minus 24. So 3x squared minus 6x minus 24. Enter. All right, I want to get that window. That window goes from, let's see, it goes, where's my window? It goes from -5 to 5. And then the y window is much larger. Whoops, actually. The y window goes from -30 to 30. I just want to make sure that the whole, oh, come on. I just want auto. There we go. Man. Telling you, I'm much better at this on my actual calculator. -30 to 30. Whew, there we go. There it is. Oh, and look at that scale. Wonderful. One more time. Give me just a second. Window. Now I really do want my x scale not to be auto, but to be 1. Really? It's the word auto. Okay. There it is. Okay. Finally. All of that I did just to verify that I would in fact have my zeros where I wanted them, right? Those zeros happening to be at x equals -2, which I just threw out of there. Let's take a look. X equals -2 and x equals 4. That was some beautiful use of technology. And again, at the end of the day, I don't really care so much about the y-intercept in that case. We just wanted to verify that, in fact, we were getting these zeros where we predicted them to be. X equals -2, right? There's -1, there's -2. That 2 is actually on the y-axis there, and then x equals 4 over there. All right, let's summarize. Go back into my full screen. Now, obviously, we're going to spend a few lessons on the zero product law because it is that important. And then we're going to see it time and time again when we solve quadratic word problems and in a variety of different settings. It is important to understand the tie between factors and zeros, all right? Whatever makes a factor equal to 0 will make an overall expression equal to 0 because when you multiply by 0, then everything is equal to 0. So it's this really unique property about 0 that doesn't work with anything else, right? There is no other number that works this way, and it gives us a really cool method for solving quadratic equations that can be factored. If you can factor a quadratic expression set equal to 0, then setting each one of those factors equal to 0 gives you the two solutions to the quadratic equation. Not only that, but we can use this technique once the equations go up to x to the third, x to the fourth, x to the fifth, etc. as long as the expressions can be factored. That actually becomes the hard part after some time. But we're going to keep looking at the zero product law in future lessons. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.